size of the universe actually grows exponentially quickly. This occurred for about 10 to the minus 30 seconds. And so you have an explanation of how you can go from a universe which is on huge scales from a region which was much smaller. But where did this inflaton field come from? Where did this scalar field come from? It's got to be from some fundamental theory.
Now that's not enough. We not only have to assume in order to make the model work, so we've already had to make one assumption, the Big Bang assumption, an unproven assumption. Now we've had to make a second assumption, that there's this inflation. Inflation caused the expansion of the universe to accelerate at this rate of doubling in size. You remember, once every billionth of a second. Now we have to assume this third thing, that this inflation is unstable. It has to be to decay. When decay should decay until the matter radiation will help. There's at least one other major amendment we have to make to the theory. We not only have to amend something about its past, we have to amend something about its present and future. And that is this new thing, which we've called, which is often known as dark energy. Now, this dark energy has to be put in by hand into your model in order to make it fit the data. It's only required you putting it in by hand in order to fit the data. So, and since they're not tightly related to one another, the theory is beginning to become more of a patchwork quilt rather than a single coherent idea that we began with. So we began with a theory which we thought was simple. We end up with a theory which actually isn't that simple. It's kind of this patchwork of ideas. The ideas don't fit together naturally. Each one has to be put in and put in just so. We don't know that the Big Bang is the beginning. That was always a hypothesis. We don't know that's true from general relativity. We don't know that it's true from our understanding of quantum gravity.
Therefore, the scale factor does not necessarily apply to space. Cosmology, based on the expansion of the universe, may not necessarily be true. We may live in a universe where electromagnetic radiation redshifts, stretching out to a maximum wavelength, then breaks down after 13.8 billion light years. The breakdown of electromagnetic radiation does not violate the conservation of energy when quantum fluctuations are taken into account.
In the infinite momentum frame, the motion of a relativistic system, when it's boosted up to enormously large momentum, behaves completely non-relativistically with respect to the motion in the plane perpendicular to the boost.
Since particles with zero rest mass can operate in an infinite momentum frame of reference, we will associate the infinite momentum frame with the period of time present time plane. Since vacuum fluctuations are suppressed in the infinite momentum frame, we will associate vacuum fluctuations with the passage of time present time plane. Quantum fluctuations relative to some inertial frame have various rates of the passage of time that decrease over an extended period of time. Relative to the infinite momentum frame, the rate of the passage of time is zero, and the periods of time and present moments correspond with the history of the universe.
Well, it turns out that empty space can weigh something. That if you actually use quantum mechanics and relativity, empty space is a boiling, bubbling brew of elementary particles, and maybe empty space can have energy. You can get rid of all the particles and the radiation, and it still weighs something.
Using this three-dimensional time model, quantum fluctuations have time reversal symmetry along the passage of time present time plane. The compactification of these fluctuations within this plane determine energy levels where pair production and annihilation have time reversal symmetry. Since the periods of time coordinate is zero in this frame, there is no arrow of time. By treating this energy state of temporal indistinguishability as a Bose-Einstein condensate, the minimal oscillation can also be treated as pseudo-Nambu-Goldstone bosons.
In the context of relativistic quantum field theory, these soft modes represent massless quantum, or so-called Nambu-Goldstone bosons. Superfluidity is the flow mediated by the soft modes, or Nambu-Goldstone bosons. And the effective theory of superfluidity can be built around that idea. So, in particle physics, we have massless quanta. In fluid mechanics, we have superfluidity. They're really the same thing.
However, quantum field theory makes predictions about zero-point energy that disagree with observations concerning the vacuum energy density of outer space.
But the problem is when we try and figure out how much it should weigh, the answer we get is 120 orders of magnitude bigger than the number that actually happened. It's the worst prediction in all of physics. And the question is, will we ever understand that? Why is the energy of empty space both non-zero and so small?
We can account for the apparent vacuum catastrophe in the similar way that we were able to account for cosmological redshift using three-dimensional time. We can argue that the vacuum energy density predicted by quantum field theory is too big because the variable rate of the passage of time is not taken into consideration. We can associate a higher rate of the passage of time with the lower vacuum energy density of intergalactic space. Though a higher rate of the passage of time is usually associated with a high temperature, the low thermal conductivity and low energy density of outer space can have a significantly higher rate of the passage of time without a relatively high temperature. This high rate of the passage of time can be associated with superconductivity.
In most cases, liquid helium is required as a cold bath to produce superconductivity. First, we want to cool the sample of tin wire. The liquid helium has been cooled below the transition temperature of tin at 1.6 degrees Kelvin. As you can see, the resistance has dropped to zero within the limits of accuracy of this instrument. Superconductivity is a state of zero electrical resistance, or, to put it the other way around, of infinite conductivity.
If we scale down the zero-point energy of quantum field theory by changing the rate of the passage of time to match that of the observed vacuum energy density, the difference between zero-point energy and the vacuum energy density becomes a function of the passage of time. For simplicity, we could write the following. Setting T double prime equal to 1 for simplicity, T prime becomes 107 orders of magnitude greater, indicating a significant difference in the rate of the passage of time between the zero-point energy and vacuum energy density. We can view T double prime over T prime as an acceleration term. If we substitute this acceleration term times the zero-point energy for lambda, we get an alternative explanation for the apparent acceleration of the expanding universe.
Paper after paper after paper has been appearing on the archives from theorists trying to explain the physics of what's going on. We were counting it is averaging roughly 2 or 3 papers every week for the past 10 years. None of them, as far as I know, would say they know what the answer is. They would say, no, they're just opening up possibilities.
corresponds to the age of the universe. A temporal definition for mass, an inversely proportional relationship between temporal coordinates, can account for the cosmological redshift of light. Different rates of the passage of time between zero-point energy and the vacuum energy density can be used to explain away the vacuum catastrophe. Using an inversely proportional relationship between the period of time coordinate and the present time coordinate, independent any relationship with the passage of time coordinate, can be used as a solution for divergences.
Here we have these Feynman diagrams which give rise to quadratic divergences in the mass of a boson. Even if the mass of the boson was initially zero, in other words, the bare mass, these diagrams would create huge masses for the bosons. That's a problem. That's a problem for all the reasons I said. We'd like to get rid of that problem. We would like to create a theory in which bosons don't get this huge amount of mass from renormalization or from whatever we want to call it?
Our standard model gives us a detailed and battle-tested picture of what ordinary matter is, based on two kinds of fundamental building blocks that technically are called fermions and bosons. In this plot, as you go to the right, you're going towards shorter and shorter distances where the unification of forces will be revealed if it occurs, and you can see that they almost but not quite meet. So, to quote Homer Simpson, no! Supersymmetry, when it's implemented in equations, requires the existence of new particles.
It's a symmetry which relates fermions to bosons in such a way that every boson has its fermionic partner, its fermionic superpartner. They come in superpartner pairs.
Supersymmetry connects all the known particles with particles that are much heavier. And this is the same picture, but with the supersymmetric particles, the partners put in.
These cousin particles have never been observed, which is a good reason to be skeptical of the idea of supersymmetry.
These new particles have not been seen yet.
Those superpartners have never been discovered in the laboratory. Not one of them, not a single one of them. The implication is these particles must be quite massive. How massive? Basically at the edge of detectability, beyond the edge of detectability. That sounds very far-fetched that we just, by accident, all the particles, all the partners happen to be too heavy to be seen, and, that really sounds like, really,
If you have a spin-a-half superpartner, you put in Eno at the end. If it's a spin-zero superpartner of a spin-a-half particle, you put an S at the beginning, S for scalar. And so there are electrons and selectrons, positrons and suppositrons, neutrinos and sneutrinos, and so on.
If for every boson we had a fermion with exactly the same mass and the same properties in every other respect, we could imagine or we could conceive that the theory might exactly cancel out the vacuum energy. So we know that, in fact, in nature, there is not this reflection of boson into fermion. If we had a theory which was sufficiently symmetric between bosons and fermions, we would at least have a chance of canceling out all this vacuum energy. So the question is there a mathematical framework that contains these kind of symmetries between fermions and bosons, which also can explain the fact that they're not exactly equal in mass in a natural way?
Unless we are using a specific rate of the passage of time to generate a mass term, we can use massless quanta to avoid changes in the rate of the passage of time. Instead of affecting the passage of time coordinate and having divergences towards infinite inertia, the infinite contributions of possible interactions can be scattered along the present moment coordinate. The spatial coordinate and the period of time coordinate are proportional. As the distance gets smaller, the periods of time get smaller as well. However, the present time coordinate gets larger such that at the limit, when the period of time interval is infinitesimally small, the present time interval is infinitely big. The present time coordinate can diverge, normalizing physical phenomena at very short distances or very high energies without generating unwanted infinities. In this case, the relationship between coordinates is inversely proportional. As the present time coordinate diverges to infinity, the period of time coordinate converges to zero. However, in terms of momentum, the relationship between periods of time and present moments, expressed through t squared, still equal 1. This allows the momentum to remain unchanged.
Now, supposing for some reason your theory was concocted in such a way that even after all this renormalization takes place, even after all the worst-looking Feynman diagrams you can imagine, that if there was enough symmetry and at every stage that symmetry was correctly preserved in detail, the cancellation of the self-energies of the bosons might also be exact.
A one-loop diagram of virtual particle pair creation and annihilation can be viewed as a time slice through a three-dimensional time loop. What makes this a time loop is the cross-conjugate relationships between forward and reverse emissions and absorptions from the vacuum. In a way, we are looking at a diagonal cross-section of a conventional Feynman diagram of virtual particle pair production and annihilation, but with the emphasis on time direction and charge. If we apply three-dimensional time to time-reverse symmetry, examining particle pair production and annihilation, we get a unique interpretation of the relationship between charge and spin. Pair production consists of particle-antiparticle pairs. A forward-time particle could pair with a reverse-time antiparticle and or vice versa. Charge could be defined as the product of the direction of spin and the direction in time. There could be four primary charges. Positive charge forward, spin with direction of momentum. Positive charge reversed, spin against direction of momentum. Negative charge forward, spin with direction of momentum. And negative charge reversed, spin against direction of momentum. Examining the conjugate pairs and cross-conjugate pairs, we see
サメドーズまで行くバスで、道のバス停に。
ピクニックバスですか。ピクニックバスはね、ここからは上に多分行かないんですよ。駅の方に行っちゃう。逆なんですよ。だから駅からの方が本数出てるんで、310円ですね。はい、どうぞ。はい。
antimatter meet, they annihilate, they explode and release loads and loads of energy, and this quite clearly doesn't happen around us. Now, in order to go from a universe which consists of half antimatter and half matter to a universe that consists of all of matter, then something really big and fundamental must have happened. And one condition for this to have happened is for an effect called CP violation to come into play. Now, CP violation is nothing more than a difference in the behavior of matter and antimatter. And quite clearly, if we have half matter and antimatter to start with, and we now have matter today, they must behave differently in order to reach that state. We don't really understand this effect, but we want to understand it in particle physics. It's a very important unanswered question in physics and particle physics and astrophysics all over the place.
If we use the standard figures, where for every matter particle there's roughly 1 billion photons, this suggests that the ratio between matter and antimatter is slanted towards matter by about, 1 part per billion. Though slight, the basic existence equations can account for this difference. If we let A represent matter and B represent antimatter, the ratio is small, but A asterisk minus A is slightly larger than B minus B asterisk. Where A and B correspond with some present moment, A asterisk minus A is slightly into the future, and B minus B asterisk is slightly into the past. It can be argued that the asymmetry between baryons and antibaryons is superficial. Forward-time baryons are symmetrical with reverse-time antibaryons, with the exception that forward-time baryons are slightly into the future relative to reverse-time antibaryons, which are slightly into the past relative to the forward-time baryons. If we allow quantum spin to be a property of three-dimensional time, then the asymmetry can be reduced to an issue of chirality and helicity. For instance, in weak interactions, fermions appear to have a preference for spin away from the direction of motion. This would allow us to cross-conjugate forward-time baryons with left-handed spin and reverse-time antibaryons with right-handed spin. But then, there was the Wu experiment, and then two unusual decays were uncovered for charged, strange mesons. In 1956, physicist Chien-Shiung Wu conducted an experiment on behalf of physicists Tsang-Dao Li and Chen-Ning Yang to wrest the relationship of parity symmetry with physical law. Radioactive cobalt-60 was cooled by liquid helium to temperatures near absolute zero and aligned with a uniform magnetic field. The thermal vibrations of cobalt-60 were reduced enough to study its beta decay process, nearly one emission at a time. Wu found that when the cobalt-60 nuclei spins were polarized with the uniform magnetic field, significantly more electrons radiated in the opposite direction with opposite spin. In other words, there were significantly more electrons with left-handed spin than electrons with right-handed spin.
The thing that's interesting is that if you measure the spin, the electrons are spinning as they come out. If you measure the spin, you find out that they're spinning to the left. That is a definite significance, that the electron, when it comes out of the disintegration, is turning this way. So all we're saying is that the right and left symmetry law is not valid. But I have to mention that conservation of parity, because you may have read in the papers that the law of conservation of parity has been proved wrong. It should have been written, because it's much easier to understand. The principle that you can't distinguish right and left has been proved wrong.
The Wu experiment shows us that the forward-time Fermi particles are able to condensate, whereas the reverse-time anti-Fermi particles are radiated away. Though this has the appearance that weak interactions have a preference for reverse-time anti-Fermi particles, the forward-time Fermi particles are able to condense first. For a slight moment, together as cross-conjugates, the forward-time Fermi particles and the reverse-time anti-Fermi particles can act like quasi-bosons. These quasi-bosons can intermediate quasi-weak interactions. The reverse-time anti-Fermi particles radiate away, appearing as electrons with left-handed spin, and the forward-time Fermi particles do not radiate away and are bound. Right-handed fermions would appear less prevalent, being bound in matter, and left-handed fermions would appear more prevalent in the form of radiation. This suggests that matter and antimatter are viewed incorrectly. We can treat the negative energy aspect of the Dirac equations as a negative time loop, treating it as a negative three-dimensional time scalar. If we plot the maximal and minimal values for t prime and t squared into three-dimensional coordinates, using t sub 1, t sub 2, t sub 3, where t prime is t sub 3, and t squared is t sub 1 times t sub 2, we quickly see that the time wave can be expressed three-dimensionally, in part using the Pauli matrices. When the time loop is expressed in the language of quantum mechanics, it satisfies the antimatter components of the Dirac equation.
There's only 3 Pauli matrices, sigma x, sigma y, and sigma z, and we need 4 matrices that have those relationships. Here's the trick. The Pauli sigma z trick is 1 and minus 1, so here we're going to have I and minus I. That gives us the extra degree of freedom. So we have 4 Dirac matrices instead of the 3 Paulis. So that says the eigenvalue for the energy for this one's mc squared, minus mc squared, minus mc squared. So you can see that the particle solution split into 2 kind of particles, 1 particle with positive energy, 1 particle with negative energy. Now, the negative energy is troublesome. We have 2 kinds of solutions in terms of the energy eigenvalues. Here is 1 pair of solutions, and here's the other pair.
The antimatter aspect of the Dirac equations may have been misinterpreted. The convention is to assume that matter is composed of particles distinctly different from antimatter, which is supposed to be composed of antiparticles. The hidden assumption of 1 time dimension locks in this interpretation of the Dirac equations. If we assume that matter consists of both particles and antiparticles cycling in and out of phase on opposite sides of a time loop, such as with an electron orbital around a hydrogen nucleus, the issue of missing antimatter disappears, and a complex relationship between time, energy, and mass appears. We could argue that matter is composed of both particles and antiparticles, but moving in opposite directions of time. Matter would be the right or stable configuration of particles to antiparticles, whereas radiation would be the wrong or unstable configuration of particles to antiparticles. Applying this to the excess baryon asymmetry equation, we could associate the excess baryons with the right configurations and the cosmic microwave background photons with the wrong configurations. This can be extended to the CKM matrix and the measurement of sin 2 beta, time-dependent parameter of CP violation in B meson decays.
For 3 families, the mismatch between the up quarks and down quarks means that the weak charge currents involve these 3x3 unitary matrices. The hadronic part is the CKM matrix. The relevant elements comes from beta decay and kaon decays and heavy bottom decays and charm decays, and beta represents the CP violation. There's 2 aspects to unitarity. The first aspect is the diagonal elements must be 1. The other aspect is that V dagger V 3, 1 should be 0. This is known as the unitarity triangle. Now, why is it a triangle? Well, these are complex numbers. Complex number can be represented as a vector in a 2-dimensional vector space. This is a vector, and that's a vector, and the last